So far, we discussed the definition of regular, irregular, singular points. Consider the following second-order differential equation: x squared minus 9 to the power 2 times the second derivative of y plus x plus 3 times the first derivative of y plus 2y equal to 0. Let us divide everything by the leading coefficient to make it into a standard form. So you end up with having the second derivative of y plus x plus 3 divided by x squared minus 9 to the power 2, which is written here, times the first derivative of y plus 2y divided by the leading coefficient, which is x squared minus 9 to the power 2, which is written here, times y equal to 0. Now take a look at the zeros of the denominator. Px and qx can be written this way. Px is the coefficient of the first derivative of y, and q of x is the coefficient of y. We can find the solutions of the denominator by setting x squared minus 9 equal to 0. We end up with two solutions. One of them is 3, the other one is -3. Now we're going to investigate if 3 or -3 are singular regular point or they are singular irregular point. Let us start by setting x sub 0 equals to -3. We need to check to see if the limit of x plus 3 times px exists as x goes to -3. So let us do the multiplication. X plus 3 times px. Px is x plus 3 divided by x squared minus 9 to the power 2. And after simplification, it becomes 1 divided by x minus 3 to the power 2. Evaluate the limit as x goes to -3. So simply because the denominator doesn't include 3, it means that we can plug in any other number into this quadratic expression on the denominator, and we get 1 divided by 36. So the limit exists. Now, let us multiply the quadratic expression by qx and find the limit as x goes to -3. So x plus 3 to the power 2 times qx, but remember qx was 2 divided by x squared minus 9 to the power 2. You can simplify this further and you end up with 2 divided by x minus 3 to the power 2. If you take the limit as x goes to -3, again you end up with a finite value. 2 divided by -6 to the power 2, or 2 divided by 36, or 1 over 18. So far we have finite values. It means that -3 is just a regular singular point. So for x equals to -3, we have a regular singular point. What about 3? Let us check 3. We do the same process. We find the limit of x minus x sub 0 times px and x minus x sub 0 to power 2 times qx. If in one of these cases the limit doesn't exist, it means that we have an irregular singular point. Take a look. Let's check the limit of x minus 3 times px, which is x minus 3, and px, as we know, defined as x plus 3, divided by x squared minus 9 to the power 2. Well, if you simplify this, you end up with 1 divided by x minus 3 times x plus 3. Now, if you take the limit of 1 divided by x minus 3 times x plus 3, as x goes to 3, since you have the factor of 3 on the denominator, it means that the limit doesn't exist. So since the limit doesn't exist, x equals to 3 is irregular singular point. Let's take a look at another example. We are making it more interesting. Now here you have x cubed minus 2x squared plus 3x to the power 2 times the second derivative of y plus x times x minus 3 to the power 2 y prime minus x plus 1 times y equal to 0. We can write this in standard form by dividing everything by the leading coefficient, which is x cubed minus 2x squared plus 3x to power 2. So we end up with the second derivative of y times px y prime, and here your qx is negative x plus 1 divided by x cubed minus 2x squared plus 3x to power 2 times y equal to 0. So this is your px and this is your qx. With the same process, we can find the zeros of the denominator and then find the limit as well. We can factor out x cubed minus 2x squared plus 3x as x times x squared minus 2x plus 3. So basically, it's written as x times x squared minus 2x plus 3 to power 2, or x squared times x squared minus 2x plus 3 to power 2. If you set this equal to 0, x is equal to 0. And for this guy, you get a complex solution. So let us analyze the behavior at x equal to 0, because this is the only real solution for this denominator. So when x is equal to x sub 0, we call it a regular singular point if the following limit exists. First of all, if we multiply x minus x sub 0 by px and x minus x sub 0 to power 2 by qx, both limits exist. If one of them doesn't exist, then we have an irregular singular point. Let's take a look. If I multiply x by px, I end up with px is x times x minus 3 to power 2 divided by x cubed minus 2x squared plus 3x to power 2. Or basically, you can get rid of x squared and x squared, and then the limit is simply can be calculated by doing substitution. The limit is nothing but 1. So basically, the limit exists when x goes to 0. Now we need to check the limit of x minus x sub 0 to power 2 times qx. Let's go to the next slide. If I multiply x squared by qx and find the limit as x goes to 0, qx is basically negative x plus 1 divided by x cubed minus 2x squared plus 3x to power 2. Simply, you can get rid of x squared and x squared. You already have x squared here, and if you factor out x from the parentheses, you end up with x squared. So now, as you can see, it's just a simple substitution in finding the limit. As x goes to 0, x squared times q approaches negative 1 over 9, which is a finite number. So the limit exists as well. So we can conclude that at x equal to 0, we have a regular singular point.